Hello, in this video we'll take a quick overview of section 4.8. In this section we're going to study Lagrange multipliers. Lagrange multipliers, if we take a look at it closely, it will rely on some level curves, or in three variables we'll be relying on level surfaces. The idea here is that to find out the maximum value of a particular function given a specific constraint, our constraint is going to be a relationship between x and y, and then our function is a function of x and y. So the function will have some z values that would denote our maximum and minimum values. Now, given a specific constraint, it turns out that if we took a look at level curves of those of the function that we're trying to maximize, and we take a look at the constraint drawn just as a relationship between x and y in the xy plane, we'll see that the level curve will be tangent to the constraint, or the constraint will be tangent to the level curve. Either way we look at it. In this case, our constraint just happens to be a line, because x plus 2y equals 7 is an equation of a line. But those constraints don't necessarily have to be lines. The point is, though, that if we look at down to our level curves, we'll see that the level curves will be tangent to each other. And what does that mean? That means that the gradients are going to be going in the same direction, or exactly in the opposite direction. In other words, they would be collinear, or they would be scalar multiples of each other. And that is exactly how Lagrange multipliers are formed. We can also take a look at this in three dimensions, or with three variables. If we have a function of three variables, f of x, y, z, that we're trying to maximize, your output is the value that we're trying to maximize. And then we have a constraint. Our constraint is a relationship between x, y, and z. We can take a look at the constraint and take a look at the level surfaces of the function that we're trying to maximize. In this case, the constraint is our ball, our unit sphere, and then we have several level surfaces that happen to be tangent planes. If you take a look at that function f of x, y, z and set it equal to, say, -1, 0, or +1, then you will have these planes. These planes are all going to be parallel because they all have the same normal vector. And it turns out that the maximum and minimum values of these planes subject to the constraint would be tangent again. And if we take a look at the tangentness of this, we're actually looking at the gradients being scalar multiples of each other. And so the equation that's needed for Lagrange multipliers is saying that the gradient is equal to some scalar, which we'll call lambda, times the gradient of the constraint. With that, you try to solve for this the best way possible. Chances are the solving for this will require some creativity, and but once you solve for it, you can check it by putting it back into the original functions to see that it is in fact the maximum or minimum. Now, those are examples of Lagrange multipliers with one constraint, and we're also going to take a brief look at Lagrange multipliers where we have two constraints. For example, we're trying to maximize a function w is equal to f of x, y, z, a function of three variables. And then we're going to deal with two constraints, a g of x, y, z equal to 0, and an h of x, y, z equal to 0. So it turns out that the Lagrange multipliers for something like this will require you to set the gradient of the function that you're trying to maximize or minimize. We'll set that equal to a scalar multiple of the first gradient and a scalar multiple plus the scalar multiple of the second gradient. And with that, you will have one equation and the two unknowns, the lambda 1 and lambda 2. We'll get three equations out of that. And then well, we have 5 unknowns, so the other 2 constraints will serve as our 4th and 5th equation. So we'll have 5 equations and 5 unknowns to solve for. Okay, so that is our overview of section 4.8, and that completes the whole chapter. And good luck. We're studying the derivatives of these functions, and in the next chapter we'll take a look at the integrals. Okay.